all seen the Lewis structure of carboxylic acids before, so I've written them out for you already here. But the Lewis structure does show that we have a resonance here. Right? So one of the resonance structures would take the set of electrons that's in that pi bond and put it up on our oxygen up here. That would give us a minus charge there and a formal plus charge down here. Now note that that's a minor resonance structure, and nonetheless it is one. And the other thing I wanted to point out is that this oxygen atom here, because we're going to see in a second that we have resonance associated with it, that it is sp2 hybridized. Okay, so if we look over at this next, the last resonance structure here, we can do this, and that would put a plus charge there. Now we could only do that transfer of electrons here, that electron pushing, if some of these electrons were in a p orbital, and they are. So these are in a p orbital, which means therefore that must be sp2 hybridized. Now, carboxylic acids can do interesting things when they're in solution. They can H bond, of course, because there's an OH, and they can also form dimers. So they end up forming these kind of interlinking structures that contribute, by the way, to carboxylic acids as having a wide stretch on IR spectra. So normal alcohols are a little bit more narrow, where carboxylic acids have a very wide OH stretch there. And that's because of this strong H bonding that's seen here. The other thing that is true of these is that they have a very bad odor. So sometimes in situations when I'm able to do this, I'll bring out a little bit of butanoic acid. And butanoic acid has a smell of kind of rancid butter. And I usually double glove, and then I grab some paper towels, and I'll not even open up the bottle, but just kind of walk around for a second in lab and allow people just to waft the odor of the bottle, and it has a very bad odor to it. So there's some interesting chemistry that we'll talk about later on in this chapter that can change the bad odor of carboxylic acids into other functional groups that smell really good, like esters. So solubility, well, it's based on carbon chain length, so up to 4 carbons, it's usually miscible in water. 5 is kind of a gray area. As we get 6 or greater, we become more nonpolar, because that nonpolar tail is growing, and that's, at some point it outweighs the polar character of the carboxylic acid. They're more soluble in alcohol, because alcohol is not quite as polar as water. We also know that they act as acids. So one thing that we saw, and this is important too, this is a lab topic, but we use the solubility switch here of carboxylic acids in doing liquid-liquid extractions in lab. So if you have hydroxide here, then what would happen is hydroxide would come around, grab that H, and then you would form, right, a benzoate molecule, sodium benzoate here. And the solubility of this molecule, you have 6 carbons, 7 carbons to 1, all right, OH there. It's not very soluble, so it's about 0.29 grams per 100 milliliters of water. So if you dump it in water, it's just not going to really dissolve unless you have almost none in there. But if you deprotonate it, whenever we have an ion in our OChem, then we basically say that molecule is water soluble. So 0.29 to 50 is about 170 times more water soluble, simply because you have that negative charge there. It makes it more polar. Now, the acidity of carboxylic acids is dependent on what type of substituents we have. So remember this, that an acid is more acidic if its conjugate base is more stable. So the more stable the conjugate base, the more apt it is to lose that H atom, right? So HA going to form H plus and A minus. If this is very stable, then we're more likely to just have the loss of an H atom, right? If it's really unstable here, then it would want to hang on to the hydrogen. It would be less acidic. So like we've done throughout the year, really, we're going to be looking at the stability of the conjugate base as an indicator as to whether or not our acid is weaker or stronger compared to other carboxylic acids in kind of a comparison type of a mode here. So any substituent here that helps stabilize that negative charge of the carboxylate ion, that'll be like this guy, right, will promote dissociation and result in a stronger acid. It turns out that electronegative atoms will enhance the strength of an acid by withdrawing electron density from that carboxylate ion. So, remember when we have that carboxylate ion, we really have a negative charge up here half the time, so it's like 1/2 of a minus charge up here, 1/2 of a minus charge down there. So sometimes we indicate that by doing this little dashed line twice and then drawing a minus charge right here in the middle. So if we just look at 3 H's that are on here, we have a delta plus that's been generated here on that carbon, right? So there's the delta plus there. And this, when you look this up, this has a pK of about 4.74, 4.8, depending on where you look this up. Now, if we take off those H's and we place chloro groups here, then what's happened is you have increased that delta plus quite a bit, because now you have this big electron pull, right, from those electronegative chlorine atoms. That bigger delta plus adjacent to this minus is a good thing. So that's what we want. And that makes our pK go down to about 0.64. Now, the other thing that your book goes into when we look at something like this is the number of chlorines will also affect that pKa. So if you have just 1 chlorine versus 2 versus 3, the pKa would go down as the number of chlorine atoms increase. And again, because your delta plus would simply be larger. And then at the other end here, we could put fluoro groups on there. Fluoros are going to be the most electronegative. That's going to give us a really big delta plus. That's what I'm trying to indicate there. Get really large dipoles, so draw larger lines there. And then your pKa goes down from 0.64 to 0.23. So remember this is an important thing. A larger partial positive on that neighboring carbon, right, that's adjacent to our carboxylic acid functional group, or the carboxylate, stabilizes that ion and makes it more acidic. So the same principle applies to benzoic acid derivatives. So let's take a look at this and see if we can explain what's going on. So let's take a look at p-methoxy benzoic acid. So just over here on the side, let me zoom in and draw this out a little bit for you guys. So if we look at that structure, right, here's your COOH, right, with our double bonds in position, and here's your CH3 here. So this structure has resonance. We drew them out, right, lots back in chapter 17, so we should feel really good with them. But right, if we look at one of our resonance structure, we're going to get that, and that would put a negative charge there, right? And then going through the rest, we'd get a negative charge here, and then we would get a negative charge down here. So when we look at the structure here, this is the position of our negative charges, okay, through our resonance structure. So we said before, it's not great to have that negative charge adjacent to our carboxylic acid. So p-methoxy benzoic acid has a pK of about 4.46. Now if you pluck off that electron donating group, because the methoxy group donates electron, then you become slightly more acidic because you don't have that adjacent negative charge to the carboxylic acid functional group. So you go down to about 4.19. And on the flip side then, we could have electron withdrawing groups. So we could have an NO2 group here. Right, so I want to take a look at that one with you guys for a second too. So let's come over here and let's take a look at that molecule and see what type of resonance we get. So remember, with that structure, that NO2, we have masked in there a positive charge. So it's a double bonded oxygen with a minus charge here and a plus charge right there, right? So what happens here is that we end up pulling electron density away. We can do this. Now that would put a positive charge right there, right? And it puts it up here. So remember, it's kind of on both shoulders and then across if you're looking for that pattern. Right? So then if we look over here, we get this. And make sure you're comfortable with drawing all those resonance structures out. So if you're rusty, go back to chapter 17 and look at that a little bit. But we'd have plus charges here. Now that's not adjacent to, it's next to this carbon. Right? So it's next to it. It's on the shoulders of it. Now if we could have it directly on that carbon that I just highlighted as green, that would be a good thing, because it would have a delta plus adjacent to where that negative charge carboxylate ion is generated. So we go to 3.47, so it's a decrease, more acidic because of that electron withdrawing group. And then if we put it at the pair position, we get even lower. Notice that's not a huge change, but it's a little bit lower there because we get that positive charge adjacent to our carboxylic acid. And then if we have it over at the ortho position, we still get the same positive charge positions here. And the pK goes down quite a bit more because the nitro group not only puts that plus charge there, but we get an inductive effect of electron withdrawing there. So it makes it a little bit more acidic. Now, carboxylic acids we've seen are acidic. Dicarboxylic acids are also acidic. They have two positions that can lose protons. So if we look at this is 3, remember, so it's O, my, so M, right, malonic acid. It has 2 Kas, so we can lose one of our H's, and it gives us this anion, and it has a Ka1 of about 2.85. It's a little bit lower because this group here is an electron withdrawing group, so it's pulling electron density away, right, than a normal carboxylic acid like acetic acid, for example, which has a pK of about 4.8. Now, losing the second proton's tougher, and that's because it's just a little bit harder to have these negative charges near each other. So it turns out as this carbon chain length grows right there, that phenomena becomes less and less. So if you threw in 10 CH2s at this position, then that dianion issue of having adjacent negative charges would be minimized as that carbon chain length grows. So they'll give you some problems like this as you go through and do your homework and stuff like that. Now the salts are typically soluble in water, and they are usually they have stronger intermolecular forces because they're ions, and they're typically solid at room temperature. And because they're solid, they make their way up to your nose a little bit less, and so they don't usually smell as bad. And then one thing that we'll see a little bit later on, which is kind of neat, we're going to talk about this saponification reaction. So we'll look at how we can take longer chain carboxylic acids and make soap and micelles and stuff like that. It's actually really interesting stuff.